Hello, this is the third part of our course, Introduction to Differential Geometry. So, today we would mainly discuss submanifolds and two related concepts, immersions and embeddings, two types of maps, immersions and embeddings. Today's discussion has two parts. The first part would be more related to definitions, examples, and theorems. Part two of our today's discussion would be more related to proof of a statement, which we would see in part one. Okay, so it would be mainly about a proof. Okay, so let's start. As I mentioned, today we would mainly discuss the notion of submanifold. What does a submanifold mean? So, loosely speaking, submanifold is a manifold inside another manifold. So, it's a manifold which is living inside another manifold. Great. Okay. So, before getting to kind of rigorous definition and careful discussion, let me tell you first of all, today we're discussing smooth submanifolds. One can discuss, say, topological submanifolds or other types of submanifolds. So we are focused on the smooth category. And let's say let's try to have a schematic picture in mind, right? Let's say this is a manifold. Let's say this torus is kind of our abstract manifold. Let's say it's called N. It's an n-dimensional smooth manifold. And let's say inside this manifold, we have another manifold, M, where this curve is presenting that. It's an m-dimensional manifold inside N. And here, M should be less than or equal to N, right? The manifold which is inside the other manifold should have less or at most equal dimension. Okay, let's look at a few examples before really getting into the definitions and theorems. So the first example, which is probably the most important example, is the local model. Okay, local model. So think about the Euclidean spaces. Think about, say, Rm inside some other Euclidean space Rn, like a line inside a plane or a line inside R3, things like that, right? We can think about Rn as Rm times Rn minus m, where here n is larger than m. Okay, so Rm times the 0, 0, 0 can be understood as a subspace of Rn. So let's say this is Rn. Let's say one axis denotes schematically Rm, the other one Rn minus m. Here Rm is sitting inside the larger Euclidean space Rn. It's like the local model of a submanifold. The same way Rn is the local model of an n-dimensional manifold, Rm sitting inside Rn is the local model of an m-dimensional manifold inside n-dimensional manifold. In the sense that any point x you pick in our schematic thing on M, if you pick a very small neighborhood of that point x inside N, it should be diffeomorphic to a neighborhood of, say, 0 in Rm sitting in Rn. So if U is that small neighborhood, if you look at the intersection of U and M, that red chunk, M intersection U, there should be a diffeomorphism which takes that to our M intersection, the open neighborhood V. So look at our M intersection V. It means when you're at X, N really looks like our N, and M really looks like our M, right? That's what it means for this Euclidean kind of case to be the local model. Okay, so there's a diffeomorphism that takes U to V and takes M intersection U to Rm intersection V. Let's look at another example. Think about the circle S1. We can define it as the set of points xy in R2 such that x squared plus y squared equals 1, right? This is, of course, naturally, the way it's described is a subset of R2. So the point is that the circle can be understood as a one-dimensional submanifold of R2. So let's say this is R2, this is the circle. So we can say this agrees with the picture we have. If we pick at any point X on the circle, if we pick a small open neighborhood around that, there is a diffeomorphism which takes this small open neighborhood to some other spot, small open neighborhood in R2, where this diffeomorphism again takes this red chunk, red piece, which is the intersection of circle with our open neighborhood, to R inside R2. Essentially, it's just flatten out the circle, right? So again, it means if you're on X, on a very, very small neighborhood, the part of the circle you see is like R, sitting inside R2. So S1 is a one-dimensional submanifold of R2, right? Okay, this is our first example aside from the local model. Let's look at another example, another simple one. Think about S1 times a fixed point, say 0, inside S1 times S1. So remember, S1 times S1 is called 2 torus, usually denoted by T2. S1 times 0 is a subset of that, right? Let's say this is our 2 torus. S1 times 0 is a curve inside this space. Let's say this is S1 times 0. So this is a one-dimensional submanifold of T2. Again, if you pick a point X on this curve, if you pick a small neighborhood on T2 around X, you can see this neighborhood is really like a neighborhood in R2. It's just flattened out somehow. That it would take the part of the curve which intersects with this open neighborhood, it takes that to R, or an open subset of R inside R2, to this red piece, right? So we have a diffeomorphism, kind of taking the open set on torus to open set in R2, taking X to 0, taking the red piece to the other red piece. We can also think about, as our third example, S1 as a submanifold of S2 and S2 as a submanifold of R3. So the way to think about it is that S2 can be understood as a set of points x, y, z in R3, where x squared plus y squared plus z squared equals 1. Of course, this is given as a subset of R3. In fact, it's a submanifold of R3, right? This is R3, and the circle, the sphere sitting here. There's a circle going around the two sphere. This circle is a one-dimensional submanifold. You can see it as saying, I define S1 to be the set of points in R3, x, y, z, where z is 0, it's an xy plane, and x squared plus y squared equals 1. That way you see it's kind of sitting inside the two sphere. Right, this is a one-dimensional submanifold of S2. And S2 itself, one-dimensional submanifold of R3. And in fact, it implies S1 is a one-dimensional submanifold of R3. Okay. Let's look at another. Well, maybe it's a good time to discuss the graph of functions. It's not an example, it's a non-example. Think about graph of the absolute value, y equals absolute value of x. The graph can be understood, well, is a subset of R2. This is not a smooth submanifold. This is kind of an example of something inside R2 that is not a submanifold. So think about R2. Let's say this is R2. And think about the graph of y equals absolute value of x. Let's say this is the graph. You see, this is a one-dimensional subspace. And this one-dimensional thing has a broken point. This red point is a broken point. Or it's a point of singularity. So it's a singularity. So this point actually is the source of the problem. The graph is not a submanifold because of this point. Any neighborhood you pick of this point, kind of the intersection with the graph looks like this, right? Looks like a wedge. There is no diffeomorphism between this open neighborhood and an open neighborhood in R2 that the diffeomorphism would take this broken piece into an open subset R sitting inside R2. So this broken thing does not look like the local model. So this is not a submanifold. It's interesting because the graph itself, if you forget about the ambient R2, the graph itself is a one-dimensional manifold. And it's just R, but it's not a submanifold. Okay, so there are different types of submanifolds. Smooth submanifolds, there are immersed ones, we call them immersed submanifolds, and there are embedded ones, embedded submanifolds. Embedded submanifolds. Okay, great. So we want to define these two types of submanifolds, immersed and embedded. In order to do so, we have to first define two notions of maps between smooth manifolds. So that's what we are going to do. This is the prerequisite to define submanifold. So let's start with immersion. Immersion. So let's say we have a map F from a smooth manifold M, let's say it's M dimensional, to another smooth manifold N, let's say it's N dimensional, and let's say the map is also smooth, everything is smooth. Okay, so I would say F is an immersion, F is said to be an immersion, this map, if it satisfies this property. I would say it's immersion at the point x in the domain if the derivative of f at the point x, which we know should be understood as a map from tangent space of m at x to tangent space of n at f of x, is injective. So if the derivative as a map between these two linear spaces is injective, I would say f is injective at x. Of course, it implies the dimension of base domain should be less than or equal to the dimension of the target. If it happens that our map is immersion at every point x in M, we would say the map is immersion. So being immersion means immersion everywhere. Great. So it's injective for all x. Derivative is injective for all x. Now, our second definition, embedding, what does it mean for a map to be an embedding? So let's say again, we have a smooth map F between two smooth manifolds M and N. Let's say this map F is a smooth immersion. So let's say it's an smooth and it's an immersion in the sense above. I would say F is an embedding. F is said to be an embedding if we look at f from M to its image inside N, so the image is f of M inside N, this new kind of codomain, if we fix that, if this is homeomorphic. So obviously it's surjective because we are restricting the target to f of M, but the more important thing is that it implies it has to be also injective. That's actually interesting. This kind of shows the notion of immersion doesn't imply being injective. We get back to this. Let's first define the notion of submanifold. Okay, we are ready for that now. Smooth submanifold. Okay, let's say M and N. Let's say M is a smooth manifold, again m-dimensional. We say M is a smooth submanifold of N if we have the following. If both M and N are smooth manifolds, that's the first thing. Second, M is a subset of N with the kind of subspace topology. Subspace topology, let's say, is compatible with the topology on M. And then, because M is inside N, there's an obvious inclusion map. M is sitting inside N. We would say M is a smooth submanifold of N if this inclusion is an embedding. So if this inclusion map is an embedding, in the sense we just defined, we say M is a smooth submanifold of N. Sometimes we kind of want to add an adjective to emphasize. We would say M is a smooth embedded submanifold of N. But if we don't say that, if we don't add extra words, we are assuming it is embedded. We have a second definition. If it happens that the inclusion of M inside N is not an embedding, but it's only an immersion. We would say M is an immersed submanifold of N. Okay, so it's a weaker notion. Great. So this shows for kind of understanding the notion of submanifolds better, we need to understand immersions and embeddings better. I mentioned that immersions don't have to be injective. So let's look at a few examples to understand this. The first thing I suggest as first exercise is that you go back and verify the examples we mentioned, like S1 inside R2, the circle inside torus. Verify these are indeed examples of submanifolds using the definition we have now. The second exercise I want to suggest you to do is to go back and look at the graph of y equals absolute value of x and verify that this is indeed not smooth submanifold. It's not embedded submanifold, it's not even an immersed submanifold of R2. Okay, so I'd like you to go that and check these two things. Okay, great. So after doing these two exercises, let's kind of think about more about immersions and embeddings. So immersions and embeddings. The first kind of example to consider for an immersion is the following. So think about the following thing. If you have a map which its derivative is injective everywhere, does it imply the map has to be injective itself? The answer is no. The simplest thing, a very simple example, is the map from S1 to R2. If we define f from S1 to R2, that f of each theta is cosine of 2 theta and sine of 2 theta, this map sends circle to R2, but it kind of goes around the circle 2 times. So of course, this is not injective, right? It sends 2 points to the same point in the target. But as an exercise, I like you to check that the derivative at each point is injective. So df at each point theta is injective. That implies the map f is an immersion. But of course, it's not an injective map. So this is the first important thing to notice. Great. Okay, so this does not imply S1 is not a smooth submanifold of R2. Note that it is a smooth submanifold of R2 because we could parameterize the circle using the map G from S1 to R2, which sends every theta to cosine theta and sine theta. This is now an embedding. So S1 is indeed an embedded submanifold of R2. It just happens that the first map we tried, F, does not give us the embedding, but there is another map G, which that function G, that map G shows S1 can be understood as a smooth submanifold of R2. Okay. So the second thing to note is that if you have smooth injective map, it does not have to be an embedding, or it doesn't even have to be an immersion. So think about the map f r to r. Simply, you have seen this map before. F of every x is simply defined to be x cubed, right? This map, of course, is injective, and of course, it's smooth. However, the point is that it's not an immersion. How is that? It's not immersion at 0. Derivative of f at 0 is 0. Well, the constant map 0 is not injective. Therefore, the function is not an immersion when x equals to 0. So being smooth and being injective, this simple example shows, is not enough to deduce that the map must be an immersion. Great. So it's a good example. Can you realize the graph of y equals x cubed as a smooth submanifold of R2? Is there different ways? to parameterize this graph as a smooth submanifold? It's a good question to think about. The next example is the figure 8 curve inside R2. Well, think about the circle S1. We can kind of construct a map that sends circle to smoothly to figure 8, right? You can just think about parameterization of figure 8. So you can kind of give a map which kind of sends, let's say, 0 and pi both to the origin. So of course this map is not injective, right? So figure 8 as a subspace of R2, thinking about that as image of F. F is an immersion, but not injective. This implies figure 8 is an immersed submanifold of R2. Right. Now, one might say maybe there was another map F from S1 to R2 such that it would have been embedding. Is that possible? So the answer is no, but we can do a bit better. We can construct a map F from R to R2 rather than S1. Let's say this is R, the infinite line. We can construct a map from this line to R2. So let's say we send 0 to 0. Let's say as we go towards plus infinity, we send the right side of the real line into this right part of the figure 8. So it kind of converges to the origin, but it never gets to the origin from the right. And as we go towards the negative number, let's say we kind of map that into the other part of figure 8. Again, as you go towards minus infinity, the other strand goes toward the origin, but it never gets there. It gets closer and closer. So you can kind of construct this map such that this map, the image, is exactly figure 8. There is no missing gap. But the map is injective, right? I mean, only f of 0 equals 0. So if f of x equals 0, it means x has to be 0. I mean, the limit from both sides, the limits are converging to 0. It's not like there is another x such that f of x equals 0. Right. So it's injective and it is smooth. Well, would that give us the fact that figure 8 is an embedded submanifold of R2? The answer is no. It still is an immersion. This is still not an embedding. So maybe let me write it as a question. So think about F. Is F an embedding or only an immersion? The answer is it's only an immersion. But the point is that if F was an embedding, if the answer was positive, it would have implied figure 8 is an embedded submanifold of R2. However, this is not the case. You can see that easily by looking at the kind of point at 0, the intersection point. If you look at that point, if you really kind of zoom in, the neighborhood of that point looks like a cross. It doesn't look like a subset of R inside R2, right? If you get a very small open neighborhood around the origin, it does not look like the model R inside R2. It looks like a cross inside R2. So F cannot be an embedding, but it's nice to kind of try to verify that directly, right? So a neighborhood of 0 intersect the figure 8 like this. And this is not diffeomorphic to open subset of R inside R2. There is no such diffeomorphism. Okay, great. So the upshot is that figure 8 is not an embedded submanifold of R2. Okay, there is an important theorem which we will get back to later. I'm not going to prove it now, but we would do that later. It's called Whitney embedding theorem. So we discussed that we usually think about manifolds in an abstract way. Whitney embedding theorem says it's okay. We can think about smooth manifolds not in an abstract way, but as submanifolds of some Euclidean space. So Whitney's embedding theorem says any smooth manifold can be embedded in some Euclidean space Rk. K does not is not equal to the dimension of our manifold. K might be a much larger number. In fact, there is a kind of bound on K. But this implies abstract manifolds, which they locally look like Euclidean space. In fact, they globally can be understood sitting inside some um, Euclidean space. So there's an actual embedding. So it's actually the case that you can think about them sitting inside some larger space. In fact, this K can be taken to be 2 times dimension of the manifold. So we will get back to this later and we will prove this. But let's just kind of accept it for now that there is always such embedding. Okay. So we kind of discussed a few things. Um, we gave a definition of smooth submanifolds using embeddings and immersions. We also kind of gave another definition of submanifolds. We said it should be at each point, very similar to the local model. These two definitions, these two things are essentially the same. Saying M is a submanifold of N if the inclusion is embedding, or saying M is a submanifold of N if at each point there's a diffeomorphism taking it to Rm inside Rn. These two things are the same. In the next part of our discussion, we are going to prove that these two things are equivalent. That if M is a submanifold sitting inside N, and this kind of inclusion is an embedding, it definitely is the case that any point x you pick on M, so let's say x is some point M on N, it definitely is the case that it has a small open neighborhood. So for every x in M, let's say this is x, there is some small open neighborhood U. U is an open neighborhood in N, which contains x. And there is kind of a local chart phi that is defined on this small open neighborhood. This chart takes you to an open subset in Rn, where n is the dimension of the ambient manifold. And phi exactly takes the intersection of U and M, this red chunk, takes exactly this part to the Rm sitting inside Rn. So in the next video, we would prove this is in fact the case. Okay? Great. So let's stop here.